All right, well, here we go with our final exam. The final, just to remind everyone, is Thursday next week. That's the 19th, right here, and it's 8 to 10 in the morning. It'll be 200 points, so about twice as long as the other exams. And pretty much you need to look at all of your other exams, put them together as best you can, and just get an idea of the kinds of things that you need to know. What we're going to do today is a set of problems. I didn't put this into an actual exam format to give you a sample, but these are questions that I would put on a sample. So this is the kind of stuff, maybe with a few extensions, that you will see on the final exam. So any questions before we get started? I hope this is recording. I had to reset the software on my computer, but I think it's working, so we'll see. All right, the exams, as you may know, always open with a section on nomenclature. So if you haven't done it yet, let's very quickly run through these guys. The sections that are going to be on the final are going to be nomenclature. There will be a section of multiple choice questions, lots of reactions, some mechanisms, stereochemistry, and then a little bit of synthesis. So our first one here, we're dealing with a cyclohexanol. It's a 1-methyl, 1-cyclohexanol. That means that we have a 6-membered ring with a hydroxyl and a methyl group on the same carbon. And across the ring from it, we have a bromine. Putting it all together, they should look something like this. Now very quickly, is this a chiral center?
No.
Of course not, because it's the same path going to the bromine on both sides. We actually could include cis-trans nomenclature here, but we haven't actually done it to that level. You'd have to specify if the bromine and the hydroxyl group were cis or trans to each other, etc. So we're not going to mess up the name with that. Our next one is a simple alkyne. It's a pentene 1-ine. So we have a 5-carbon chain with a triple bond in carbon number 1. We also have a double bond in carbon number 3. Putting it together, it should look something like this. 1, 2, 3, 4, 5. 5 carbons, triple bond in carbon 1, double bond in carbon 3. Cyclohexadiene 1-ol. Remember, the hydroxyl group is going to be the highest priority, so that's going to be position 1 on the ring. We have a 6-membered ring with 2 double bonds, and relative to the hydroxyl group, they are at carbons 2 and 4. So we start off by drawing our 6-member ring, put the hydroxyl in, and then at carbons 2 and 4, we put in 2 double bonds. Nice simple set. Any questions? Well, let's make it a little more interesting and put in some RS stereochemistry. Here we're dealing with a simple compound, a 2-butanol. We have a 4-carbon chain. In carbon number 2, we're going to have a hydroxyl group. We need our stereochemistry there to be S. Now, kind of the way I do these things, if you're going from a name to a structure, is I will draw the thing, and then I'll figure out if we're doing, if what I've drawn is R or S. If it's the wrong one, it turned out to be R, I would just swap a couple of substituents and we'll be set. So, we have this 1, 2, 3, 4, so there's our bute. In carbon number 2, we have the hydroxyl group, so it's a 2-butanol. Now, let's check it to make sure that this is in fact S stereochemistry. Our priorities: hydroxyl group is going to be number 1, the ethyl will be number 2, and the methyl will be 3. Our lowest priority group, the hydrogen, is facing forward. So, as we look at our order here, we're going 1, 2, 3, so that's that way. That's clockwise, isn't it? Clockwise is R, but only if the lowest priority is facing back. So clockwise, with the lowest priority facing forward, is in fact S. Do you have a set of the handouts? Anyone need one? Okay.
Yeah.
There was one set left. All right, our next one, we have a cyclohexane ring. It's a diol, so we have 2 hydroxyl groups. They are trans to each other, and they are at positions 1 and 2 on the ring. Well, that's 1 and 4 on the ring. So either change the question to 1, 4 or the answer to 1, 2. If this, in fact, was the correct structure, they would both be equatorial in the 1 and 2 positions, or both equatorial in 1 and 4. Sorry about that one. Our next one, moving on quickly. We have a substituted benzene. Our substituent is a chloroethyl group. Now, a chloroethyl is simply a 2-carbon unit. It's attached at carbon number 1 by definition. And attached to carbon 1, we also have a chlorine. So we have a benzene ring, we have a 2-carbon chain. In our first carbon, we have a chlorine attached, and we need S stereochemistry. So let's draw it like this, and let's try to figure out if this is correct or not. Our highest priority, of course, is going to be the chlorine. Our next is going to be the benzene ring, and our third here is going to be the methyl group. Our hydrogen is pointing forward, so we're going to reverse whatever answer we get. This looks clockwise to me, but again, this is facing forward, so this is in fact S stereochemistry. Let's do a couple more. We're dealing with a pentyne 3-ol. So we have a 5-carbon chain. The 5-carbon chain, well, the 5-carbon chain has a methyl group in carbon 3. It has a triple bond in carbon 1. And it has a hydroxyl group in carbon 3 as well. Putting these together, here's our 5-carbon chain, 1, 2, 3, 4, 5. Triple bond in carbon 1, methyl and hydroxyl in carbon 3. very quickly look at this just like we had before and decide if this is in fact S stereochemistry. Our highest priority is a hydroxyl group, followed by our triple bond, followed by our ethyl group. So our lowest priority here is going to be the methyl, and fortunately it is facing back. So our groups look like this. We're going 1, 2, 3 counterclockwise. This is in fact S configuration. And our last example for nomenclature, 5-methyl-hex-2-ine. So we're dealing with a 6-carbon chain. In carbon number 2, we have a triple bond, and in carbon number 5, we have a methyl group. No stereochemistry to worry about. It simply looks like this. 1, 2, 3, 4, 5, 6. There's our parent. 2 alkyne, 5 methyl. Any questions? You will have nomenclature like this, maybe 2 or 3 more, and just about this degree of difficulty. Any questions? All right, like I said, everyone loves taking the quizzes so much that I thought I would put some of the quiz questions, multiple choice quiz questions, also on the exam. Here, yeah.
Will you open up quiz 3 again, or no?
Yes, I'm going to open up everything for one more attempt, okay? Everyone gets one more attempt between now and the final, but just one. All right, which of the following is true regarding an SN2 reaction? Okay, remember SN2s. Rearrangement commonly occurs. Nope, 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 nope. We don't have carbocation intermediates in an SN2 reaction. Intermediate radical. Nope, we don't have radicals in an SN2 reaction, do we? Most stable carbocation. Nope, no carbocations in an SN2. A and C only, that's not looking good. And the answer, of course, is the dreaded none of the above. Any questions? SN1 reaction. What do we know about that? Concurrent E1 elimination are common. Well, we know that an SN1 involves a carbocation intermediate. So the first step, the slow step, in an SN1 and an E1 reaction is the same, isn't it? So this is a very viable answer. Rearrangement of the carbocation is common. Well, we have a carbocation, sure. Rearrangements are going to happen. Reaction is favored by polar protic solvents. Well, if you're going to make ions, a polar solvent is what you want to stabilize the ion. So it sounds to me like all of these are correct. Any questions? An important thing to remember about this is what I said, and that is that the rate limiting step, that is a slow step, for the E1 and the SN1 is the same thing. That's loss of the leaving group, that's the slow step in both mechanisms. All right, E1 again. Because of steric effects, the least substituted alkene is typically formed. No, that would make site-step very unhappy. We always try to shoot for the most highly substituted alkene. Elimination occurs in a anti-periplanar manner. No, that's an E2 reaction, isn't it? In an E2 reaction, the hydrogen is removed, it's trans or anti to the leaving group, and they must be coplanar. But that's an E2, not an E1. Hindered bases tend to favor elimination over substitution. Well, yeah, that makes sense. Because you get a big, fat, ugly base that can't get in there and substitute. All it can do is yank off a hydrogen. This is clearly the best answer. All right, here we have a simple reaction. We know if we take an alkyne and we treat it with BH3 and THF, that we form an intermediate borane. Now actually there are two reactions of that borane. One that we've talked a lot about and one that's mentioned briefly in the book because it typically is a side reaction. If you take that intermediate borane and you dump it into water, you wind up with reduction. So it goes from an alkene or an alkyne all the way down to the hydrocarbon. Here, let's look at our options. A is work up with aqueous acid, will yield an aldehyde. Let's see, alkaline peroxide yields a rearranged ketone. We have no rearrangement. Borane intermediate, the boron will be bonded to the benzyl carbon. No, because it's anti-Markovnikov, isn't it? I actually changed this one. I forgot to change this to aqueous base. So change that one on your sheet. So this is simply hydroboration oxidation. Sorry about changing that. Because this was originally written for the dump into acid, make the hydrocarbon, but we haven't covered that one. All right. This is a cute question. You have an unknown compound. We dump in acidic potassium permanganate. We wind up with a carboxylic acid and CO2. Now what we're doing with the acidic permanganate is we're cleaving either a double or a triple bond, right? Because we wind up with CO2, that means that this is either a terminal alkyne or a terminal alkene. The carbon on the end is cleaved all the way to CO2. The other carbon goes to the carboxylic acid. So our options here, tetrasubstituted alkene. No, because if we had that, we would cleave it in half and make two ketones. Disubstituted alkyne, that would give us two carboxylic acids. Trisubstituted alkene, that will give us a carboxylic acid and a ketone. Trans-disubstituted alkene, that makes no difference. This is the only one that works, a terminal alkene with one alkyl substituent. So what we're dealing with is this. We must have a terminal alkene or alkyne. We must have at least one group attached to it on one side, because this is the one that's going to be the carboxylic acid. Our permanganate is going to cleave it right here. This carbon is CO2, and this one is our carboxylic acid. Any questions?
So we have to really look at the mechanisms then and really understand terminology and all.
Sure. Of course you do. All right. Let's go and do some simple reactions here. We know 3 or 4 groups of reactions. We know reactions of alkenes, alkynes. They're pretty much the same thing. We know reactions of alcohols, and we know substitution, elimination. But really, that's all we have to deal with, right? Each of those will have substitutions, oxidations, and whatever involved. But here we have acidic permanganate. Now, we just talked about acidic permanganate. What does it do?
Leaves.
It cleaves bonds, doesn't it? So we have a double bond here. We are going to cleave this double bond right here, like that, with our acidic permanganate. Now what's attached here? This has an alkyl group and a hydrogen. So it's going to go to what? What did it go to in the previous problem? It goes to a carboxylic acid. This guy also has an alkyl group and a hydrogen. So that carbon also goes to a carboxylic acid. Putting it all together, we get this. Carboxylic acid on both ends. We have 1, 2, 3 CH2s between them. So 1, 2, 3, and that's what it looks like. All right, this is the one that we messed up on the couple slides ago on the multiple choice question. This is hydroboration oxidation. We know that we're going to form an anti-Markovnikov addition product. Because this is a triple bond, that will be an anti-Markovnikov enol. So we're going to put a hydroxyl group on this carbon. This is the anti-Markovnikov carbon. That hydroxyl group is going to spontaneously rearrange from the enol to a carbonyl. Now, because we're bonded to a hydrogen here, this is going to be an aldehyde. All right, one of the very first reactions we ever did. Alkene plus HBr. What do we know about that? Well, it's stepwise, isn't it? It has a carbocation intermediate. We can get rearrangement, and the bromine will add to the carbon that forms the most stable carbocation, that is Markovnikov addition. That carbon would be the tertiary carbon right here, so all we're making is this addition product. Simple Markovnikov addition. All right, there was a little bit of confusion in everybody's mind about sodium and liquid ammonia. Remember, we know 2 reactions, this one and this one. When sodium is dissolving in liquid ammonia, it bubbles. That's hydrogen gas. Well, the process of making hydrogen gas involves making hydrogen radicals. The hydrogen radical is what's going to add to our triple bond. It adds one at a time. So we add one hydrogen radical, wait a second, add the other. Because of that, the molecule is going to form its most stable conformation, which is always trans. So, what we're going to do is add hydrogen here. We're going to wind up with a trans alkene. Remember, it bubbles. When it bubbles, hydrogen radicals. Next semester, you'll meet several other reactions that also involve dissolving metal. Same thing, hydrogen radicals. Ozonolysis, followed by workup with zinc dissolving in acid. So that's again a reductive workup. Ozone, just like permanganate, will split a double bond. When it does, all you need to remember is you take each carbon and make it a carbonyl. That's all you have to remember. Ozonolysis splits and we get 2 carbonyls. This one is going to be formaldehyde, this one will be benzaldehyde, and the pair looks like that. Now this next one, this is sodium previously dissolved in liquid ammonia. All right, so you dissolve it, you wait till it finishes bubbling. Then you have a solution of sodium amide, very strong base. Now sodium amide, because NH2- is such a strong base, is going to pull off the hydrogen, the proton, from our triple bond, that is our alkyne. We go from the alkyne to the alkyne anion. Now the alkyne anion is our nucleophile here. So after step 1, we have our anion. Here we have an alkyl halide, benzyl halide actually. This is simply going to attack in an SN2 reaction, displace the bromine, and what we've done is to simply tag the carbon portion of our alkyne onto our benzyl group. Simple SN2 substitution. Step 1, we make the anion. Step 2, we use that anion as a nucleophile. Any questions? All right, thionyl chloride. We know 2 reactions of thionyl chloride. We get a slightly different mechanism depending on whether or not we are in a nonpolar solvent or whether we're in something like purity. In a nonpolar solvent, we remember we are going to have an SNI reaction. I is intramolecular. And we get retention of stereochemistry. What we're going to do with thionyl chloride is simply change the OH group to a chlorine. When that happens, all we have to do is yank off the OH, stick on a Cl, same configuration, and it looks like that. Retention of configuration. Pyridinium chlorochromate in dichloromethane. It's an oxidizing agent. The actual oxidant is CrO3, but it's a very, very mild conditions. When you make the pyridinium chlorochromate, very, very mild oxidant. It's going to oxidize the hydroxyl group to a carbonyl. But because it's so mild, it will stop after 1 oxidation step. We have a hydrogen attached here. That means we're going to oxidize this to the aldehyde. Any questions? All right, PLCO3 impurity. PLCO3 is going to react with our hydroxyl group, and we're going to get an intermediate chlorophosphate ester. What we've done is we have made our hydroxyl group a good leaving group. Now, in the presence of something like pyridine, pyridine is a nitrogen compound. It acts as a base. So what we're going to do is a simple elimination reaction. It's going to be a very nice, civilized E2 elimination. Now remember, SciSef told us we are going to always get the most highly substituted alkene. That means we're going to make a double bond across here, not here. Product is simply this. Hydroboration oxidation, once again, nope. Hydroboration, dump it into water. Really, this reaction kind of happens by accident. If your THF tetrahydrofuran it's an ether, you can always also use it with Grignard reagents. But it's an ether, and as such, water has a fairly decent solubility in THF. So because of that, if you have wet THF, when you go and do your hydroboration, you wind up with the hydrocarbon. So you have to be really careful not to let that happen. If you do it on purpose, we would form borane. When we dumped in mildly acidic water, we would go all the way to the alkane. pH3 is a little bit difficult to handle. So this particular reduction isn't done a lot. There are easier ways to reduce. We have an alkene. We have HBr peroxide. What do we know about that? We know that we're going to make the bromine radical. Bromine radical is going to add to our double bond to form the most stable radical. That's going to pick up hydrogen to give an alkyl halide. Now, radical stability, we know, parallels carbocation stability. So our tertiary radical would be more stable than our secondary. So that means the bromine radical is going to add here. We will pick up a hydrogen here, giving us anti-Markovnikov regiochemistry. And it would look something like that. Any questions? We'd actually get a whole bunch of stereoisomers here, but we don't want to deal with that. Good luck. Thank you. Here we have an alkyne and an alkene, and we have hydrogen gas and platinum as our catalyst. We know that platinum, typically on the surface of charcoal, so you have something that way out, is a very powerful catalyst. Same catalyst, same type of catalyst you have in a catalytic converter. This will reduce both a double bond and a triple bond all the way to the alkane. Therefore, we're just going to wind up with a simple alkane as our product. Any questions? can make a Grignard reagent out of an alkyl halide, a vinyl halide, or an aryl halide. Here we started off with a vinyl halide. So that means here where the magnesium is attached now, just the bromine was attached to this carbon. Okay? So we have our Grignard reagent. We're simply reacting that with an aldehyde. All in the world that's going to happen is that this carbon, because it has carbanion character, is going to be our nucleophile, going to add to the carbonyl carbon to form an alcohol. Because it's an aldehyde, that will be a secondary alcohol. And the product should look like this. The aldehyde hydrogen isn't shown, but it's attached here. This is the chunk we put on from the Grignard, this 3-carbon piece. This is the 2-carbon piece that was our aldehyde. PBr3, all PBr3 is going to do is convert an alcohol to an alkyl bromide. We remember that this is an SN2 process. And because of that, we will get inversion of configuration. So what we need to do is simply take our starting alcohol. We're going to convert the OH group to a bromine, and we're going to invert our configuration. What I've done is I've moved the hydrogen to the front, put the bromine in the back. That's a simple inversion. If you want, you could sit and do RNS on this. With this one, it's easy. Hydroxyl, phenyl, methyl. So that's going this way, that's clockwise. That makes it R. Here, our hydrogen is forward. So we go 1, 2, 3. We invert it because this is forward. This is S configuration now. So we've gone from R to S. I'll point this out again later, but note the process here. We want to show an inversion, right? All you have to do to invert the stereochemistry. This is R, we said. R. Yeah, that's R. If we wanted to draw this as S, all we'd have to do is swap any 2 groups. Any 2 groups. And that gives us the inversion of the configuration. All right, we have a formate ester. We have 2 moles of methyl magnesium bromide. Remember when we react an ester with a Grignard, the alkoxy is gone. We never see it again. Doesn't show up in your product. We add 2 of our methyl groups here to the carbonyl. This is a hydrogen attached, so we're going to get a secondary alcohol. 2 of these guys on, none of this, and it's simply 2-propanol. Sodium, actively dissolving in liquid ammonia. It's bubbling, it's fizzing. This is reduction. We're going to reduce our triple bond to a trans-alkene. We already have 1 alkene in our product. Sodium and liquid ammonia won't touch it. So all we have to do is redraw this as a trans-alkene. I remember way back when we did reactions of alkenes. We found that there was a simple way to make cyclopropane addition products. We use here diiodomethane, zinc copper amalgam, it's called. When you do that, all we're going to do is take this CH2, convert it to carbene. Remember, carbene is neutral. CH2, neutral, but it's very, very reactive. It's going to come and add to our double bond, and we simply make a cyclopropane ring right here on the double bond, and this is the product we get. Any questions? All right, this next guy, this is an elimination reaction, isn't it? We have terbutoxide as our base, big hindered base, so we're going to get a nice E2 elimination. We're going to form the most highly substituted alkene. Let's say so. That means we're going to get a double bond right here, which means we have to pull this hydrogen off, and the iodide has to leave. Now, let's just think about what we've got. In this stereochemical picture, we have the iodine and the methyl going back, and these guys are all coming towards us. If we did this in a sawhorse, it would look like this. Iodine down, methyl down, those guys. And these guys are all pointing up. We're going to do an E2 elimination, aren't we? In order to do that, remember the hydrogen we pull off must be trans to our leaving group. Therefore, I'm going to take this and I'm going to rotate it so my hydrogen is up, so it's trans to the leaving group. There it goes. All I've done is just rotate that 60 degrees. Now, our hydrogen and our leaving group, the iodine, are trans to each other. When our base comes in, remember our base is terbutoxide, all that's going to happen is it's going to pull off this hydrogen, iodine's going to leave, we will wind up with an alkene. And the alkene, well, both of these are methyl groups, so it doesn't really matter. And we have an ethyl and a CH3. This is the product right here. Make sure you remember the mechanism here of the E2 elimination.
Professor, are we ever going to have an example where we have to show stereochemistry?
Yeah, probably.
We will.
Yeah, we'll see some of those in just a minute.
I have a question.
Yeah.
On the last example, the iodine and the hydrogen, aren't they already trans?
No, in our initial thing here, remember this is going back, this is going back, this is coming forward. So they have to be in the same plane. They have to be trans-coplanar. So we take this, we rotate it, so now it's perfectly coplanar with this guy, and the elimination can occur. Also called anterofacial, opposite face. All right, simple substitution reaction. We have methoxide and we have benzyl bromide. You will come to appreciate next semester when you do conjugated systems just exactly why the benzyl group is so reactive in things like SN2 reactions. Methoxide is simply going to attack, bromine is going to leave, and we're going to make the ether. trivial reaction. Here I've just taken a different nucleophile, still an oxyanion. All that's going to happen is the oxyanion is going to attack, bromine is going to leave. This is also a good reaction. Why is this almost as good as the benzyl? We have a special name for this type of carbon, don't we? That's allylic. Remember, a carbon adjacent to a double bond is an allylic carbon. Oh, I forgot to do the reaction. So, the oxygen attacks, bromine leaves, and in this case we get the ester. Speaking of allylic carbons, in bromosuccinimide in carbon tetrachloride, shine a light on it. H nu means light. We know we're going to form an allylic radical. Allylic radicals are very stable. The allylic positions here are the carbons adjacent to our double bond. So this guy or this guy, they're both allylic. We will wind up with a bromine attached to one of those. Lots of reactions, right? Here we have thionyl chloride, but this time we put it into pyridine. When we see thionyl chloride and pyridine, we say to ourselves, oops, this is inversion of configuration. So we want to redraw our starting material, change the hydroxyl to a chlorine, and invert our stereochemistry. All we have to do to show inversion is to swap two groups, and that will work. Once again, we have an ester, and we have 2 moles of methyl magnesium bromide. The methoxy group here is going to be gone forever. We're going to add 2 methyl groups to our carbonyl carbon. When we do that, we're going to wind up with a tertiary alcohol that looks like this. Remember, these 2 groups right here came from our Grignard reagent. Lose the alkoxy, add 2 Grignards to the carbonyl carbon. Our next one, we simply have a ketone. Next semester, you will refer to this as an alpha-beta unsaturated ketone, conjugated system. But this will react with methyl magnesium bromide. We'll stick 1 methyl on this carbon. Again, we have a tertiary alcohol. Only 1 of the methyl groups comes from the Grignard, however. We have chlorocyclohexane and we have hydrogen sulfide anion. Sulfur is a very good nucleophile. As you go down a group in the periodic table, it gets, the nucleophilicity goes up. So this is more nucleophilic than the oxygen would be. All that happens is a simple SN2 reaction. Sulfur hits here, chlorine leaves, and we wind up with the thiol. Thiols you don't know for a fact, but if you go on in chemistry, thiols stink horribly. Essence of skunk is a thiol, etc. Some thiols, once you get them in your system, it takes months to finally breathe it out of your lungs. It's horrible stuff. HBr peroxides, we know this is going to give us an anti-Markovnikov alkyl halide. Our most stable radical would be here in our tertiary carbon. That means the bromine is going to add here, and that's our product. And finally, let's wind up with a reduction using Lindlar catalyst. Lindlar catalyst is a poison catalyst. So you start off with perfectly good platinum. You dump in something like barium sulfate. The sulfur will chelate to the platinum, makes it a lousy catalyst. But because it's reacting with an alkyne, which is very reactive, you can still do one reduction. Just like reduction of an alkene, both hydrogens are going to come in from the same side, so we wind up with a cis alkene. Now there's lots of reactions here, but we've done lots of reactions in our last couple of exams. You should be familiar with how to do them, because please make sure you are, because they're going to be a lot, just like this on the final. Let's just make this a little bit different. We're going to do elimination reactions here, but we're going to double it up. Not just do our elimination, we're also going to name the product that we form. Some kind of a combination question. All of these are terbutoxide and terbutanol, so they're all E2 eliminations. Remember in an E2, our leaving group and the hydrogen that's removed must be anti to each other and in the same plane, anti-periplanar. Here we're going to yank off the hydrogen. Bromine's going to leave. We're going to form the most highly substituted alkene. Going to be right across here. That's all we make. Trivial reaction. Now this guy. If I gave you this one, you would have to think about it. Because we have chiral centers here and here, don't we? That means it's going to make a difference how we do this elimination. So I would do this, stepwise. First thing I would do would be to draw this in a sawhorse, like we did previously. Oh, I didn't name it, did I? 1-methyl cyclohexene. All right, this guy. Let's take and convert this to a sawhorse. Now with the sawhorse, bromine and the ethyl group, this guy and this guy, are both down. The other two groups here, all these are facing up. Now, in order to do our elimination, we have to take this hydrogen and move it so it's anti-periplanar to the bromine. So all we have to do is rotate this carbon so the hydrogen is facing up. Now, I assume that you can do that on scratch paper. I hope so. I can do it with a click of the mouse. There. So now our hydrogen and our bromine are anti and periplanar. we can simply take a base, yank the hydrogen off, make our double bond as the bromine leaves. Now, the product that we make, take a look. Ethyl is going to be on this side of our double bond. This ethyl is on this side of the double bond. That means our ethyl groups are trans to each other. Make sure you see that. Our ethyl groups here are on opposite sides of our double bond. Therefore, they are trans. And our product just looks like this. Two ethyls are trans to each other. Yeah.
Could we keep our product in the solid worst form?
Could you keep, yeah, as long as I could tell what's what. You know, any decent drawing would do. Our stereochemistry here, because this is trans. Trans is also E, isn't it? This is a 6-carbon chain, so it's a hexene, double bond in carbon 3. In carbon 3, we also have a methyl group, so it's E, 3-methyl, 3-hexene. Our last one. Well, this looked like it was set up for us, but it's not quite set up as nicely as we thought. We have to rotate, so this bromine is down opposite this hydrogen, correct? But you know, that doesn't really matter because we don't have chiral centers on both carbons. These are 2 methyl groups. So we're not going to have a cis-trans stereochemistry. Therefore, all we have to do is eliminate HBr, make a double bond, and it looks like that. You only have to worry about the stereochemistry here when you're dealing with chiral centers. Our name, well, this is simply a 1, 2, 3, 4, so it's a bute. It's a 2-butene with a methyl group in carbon 2. 2-methyl, 2-butene. Any questions? All right, so this is a nice representation of all of, most of, the reactions that you know. So, again, if you know this set and you can come up with all of these products and you can think about stereochemistry and stuff, you're actually in pretty good shape. Now, another thing that we learned this semester was mechanisms. Here we have a simple alkene reacting with HBr. We know that this is going to give us a carbocation intermediate. That carbocation can undergo rearrangement. We're going to add the bromine when we're all done with that stuff to make an alkyl bromide. In this problem, you are asked to draw the initially formed carbocation. That will undergo rearrangement to form the most stable carbocation. That will simply add bromide to give our final product. All right, our initially formed carbocation is going to be here on our secondary carbon. Therefore, in our first box, we would simply draw this. Carbocation on our secondary carbon. Now, This is going to undergo a rearrangement. On this type of problem, what I want you to do is to show the rearrangement using your curvy arrows. The rearrangement we're going to do here is going to be a 1,2 hydride transfer. That is, hydrogen with its electrons is simply going to slide from here to here. When it does, we will go from our secondary carbocation to our tertiary carbocation, which is our most stable. Again, on the exam, you should show curvy arrows, hydride sliding over. If your artwork is really bad, you could write hydride shift, just so I know what you're talking about. Finally, once we have the most stable carbocation, all we have to do is add bromide, and our final product looks like this. Any questions? Another mechanism question. We know that if we react an alkene with HOBr or HOCl, we will form a halohydrin. A halohydrin will have an OH group on one carbon and a halogen on the other. The hydroxyl group will bind to the carbon to give the most stable carbocation. So it's Markovnikov with respect to the hydroxyl group. Hydroxyl group is going to bond to this carbon, therefore, and the bromine here. Now, in this problem, you are asked to draw the bromonium ion. Remember, just like in the addition of Br2, first thing that happens is Br plus, effectively, will just sit down on top of this pi cloud. When it does, it forms this cyclic intermediate we call the bromonium ion. And it would look like that. Br, simply sitting on our pi cloud, is a little three-membered ring. Has a positive charge, that's why it's called a bromonium ion. Now the second step in this reaction, which you should also show on the exam, is hydroxide, OH minus, is going to attack. Going to be an SN2 style attack, and it's going to attack the carbon that would form the most stable carbocation. So that's our tertiary center. So what happens next is hydroxide is simply going to come in, attack here, our ring opens, and we wind up with the trans halohydrin. And that would be a perfect answer on the exam. Another alkene, and we're adding HCl. We know we're going to get a carbocation. If it can rearrange, it will. Obviously, it can. We will form the most stable carbocation. We will add chloride to make our final product. Now, our initially formed carbocation is going to be on one of these secondaries, but it only makes sense to put it here next to the quaternary system. It's actually a more stable spot anyway. But therefore, all we have to do for our initially formed carbocation is to draw this. Now, we can't do a hydride transfer here, but just like hydride can slide over, here an entire methyl group is going to slide from one carbon to the other. And that's going to go from our secondary carbocation to a tertiary. So, we would show it something like this. Methyl group simply slides over from here to here with its electrons, leaving this center, now the carbocation. We have a stable tertiary carbocation, and everybody's happy. This is simply going to add chloride to this point, and that will be our final product. One more mechanism. We talked about hydrochloration and oxidation. We know that this gives us anti-Markovnikov regiochemistry. We also know that we have syn addition, that is same side addition of the hydrogen and the hydroxyl group. So that's what we know. Here we're asked to form or show the borane intermediate. This is then going to be plunged into alkaline peroxide to give our final product. Now, our borane intermediate is going to form such that the boron is attached to the anti-Markovnikov carbon. So we look at this. Boron is going to attach to our secondary center, hydrogen from BH3 to the tertiary. And they will be on the same side. Therefore, our intermediate would look like this. Boron on the secondary carbon, hydrogen on the same side of the molecule, but here on the tertiary carbon. Now when you're drawing borane intermediates, you actually don't have to show what's attached to the boron. In reality, this thing BH3 will react with 3 moles of alkene, so you'll have a huge ugly mess down here with lots of stuff. All we really care about is where the boron is attached. The actual magic of the oxidation that gives us this, you don't have to worry about that mechanism either, although it is in the book. But the OH group is simply going to replace the boron exactly where it sits, and our final product is the anti-Markovnikov alcohol. Remember, the hydrogen and the hydroxyl group are on the same side of the molecule. All right, that's mechanisms. On the exam, you will have mechanisms. On this last exam, we did enol conversions. We also did ester substitutions, that sort of stuff. Those are all considered mechanisms. Okay? Stereochemistry, chapter 5. Let's start off with a very simple one. Look at these molecules. Either indicate that they are achiral, meso, or if they are chiral, just give me the number of chiral centers. Our first molecule here, the only thing, well, the only two that would possibly be would be this guy or this guy. Oh, we have two bridges here that are both 2 carbons. Those are identical bridges. Therefore, both of these are attached to the same thing. This molecule itself has no chiral centers. It is achiral. Our next guy looks really complicated, but of course it is not a chiral center, is it? Because up here we have a cis alkene, a 3-carbon unit that's cis. Down here we have a 3-carbon unit that's cis. Same thing. This is an achiral molecule. Now this one. We have a chiral center here, here, and here, and here. So we have chiral centers everywhere. But if you look at it, right across here, we have a plane of symmetry, don't we? If we drop the mirror straight down, this carbon and this carbon will be the reflection of each other. Therefore, this is a meso compound. Now this next guy is a little more challenging. It does have chiral centers, 1 and 2. So, we either put the number 2 or it's meso, right? Let's test whether this is meso simply by doing R and S on each of these centers. Okay? Here is our molecule, blown up. Our highest priority group for the top is going to be the hydroxyl group. This is going to be carbon number 2. This is going to be number 3 in our priorities. Now our hydrogen is our lowest priority and is facing forward. Therefore, whatever answer we get, we're going to take the opposite, right? So this is going this way. That's clockwise. Clockwise is R, because hydrogen is forward. This is S, stereochemistry. So our top carbon is S. Our bottom carbon, highest priority, going to be the hydroxyl group, then the secondary carbon, then the methyl group. Hydrogen is down, it's back. Therefore, this is going clockwise. This is R configuration. Whoops. Because we have S up top, R in the bottom, that makes this a meso compound. Let's go back to this. Remember, in a meso compound, we have an internal plane of symmetry, an internal mirror. The reflection of S is R. Therefore, if you have a molecule like this with 2 chiral centers, one is S, one is R, they have the same substituents, that tells you it's meso. This guy. Both of these carbons have different substituents, so both of these are chiral centers. Same thing we did before. Here, bromine is going to be our highest priority, then this guy, then this guy. This one is an R configuration. This one down here. If you look at it this way, you should be able to see in your mind, bromine going up here, then down to methyl. That's that away, that's S configuration. Again, R and S are mirror images. If you want, you could take and draw this like we did before, stand it up, and do it, but sometimes you can just do this in your head. I don't. Our next one here. Lots of little groups, but we have methyl groups. They are 1 and 3 relative to each other. They are both cis. If you think about it, if you wrote this planar, flat, it'd be real easy to see that you could put a mirror plane right through here. The two methyls would reflect, and everything else would too. Simple meso compound. Draw it flat if you have any questions. 2 more in this set. 3 more. Trans, 1,2, dimethyl cyclopropane. Both of these are chiral centers. However, there is no mirror plane. The mirror plane would go down here, and hydrogen and methyl are not the reflection of each other. Therefore, this has 2 chiral centers, and it is not meso. Our trimethyl cyclohexane. Once again, there is no plane of symmetry. Each of these is a chiral center, not a meso compound. And finally, our little flying wing here. Both of these are cyclopropane groups sticking up. Therefore, they're identical, and this is an achiral molecule. Remember that when we're talking about a meso compound, it's also proper to say that the meso compound itself is achiral. It contains chiral centers, but the molecule itself is achiral. Important distinction. All right, we're going to do 2 simple substitutions here. All I want you to do is draw the product. These are SN2 reactions. What do we know about SN2? Well, we're going to get inversion of configuration, right? In this case, the oxygen is going to attack, the bromine is going to leave. You know, maybe the easiest way to do this would be just to draw it like this. So I'd simply replace the bromine with the nucleophile. Now, this does not show inversion, does it? In order to make inversion, I would do this on scratch paper, and then I would just swap any 2 groups. Any 2. And when I do that, I now have inversion. Scratch paper. Just substitute the nucleophile for the bromine. Step 2, just pick any 2 groups and swap them, and you have inversion. Any 2 groups. Oh, I'm sorry, I couldn't tell what was happening here. Just to prove that we do have inversion here, I also put this in. Bromine is 1, this is 2, this is 3, hydrogen is back. Therefore, this is S configuration, right? This thing that we've written over here, hydrogen is back, oxygen is 1, that's 2, that's 3. This is R configuration. So we have, in fact, done inversion. All right, this next one is really simple. We have a cyclohexene with an iodide in the allylic position. We're reacting this with phenoxide, oxygen nucleophile, iodide leaves. We have to show inversion. Here I've just swapped the oxygen, would be here, with the hydrogen to make this inverted product. Any questions? All right, this is a neat question. Here we have an alkene. We're reacting it with permanganate and base. What that does is form a cis 1,2 diol, right? What I want you to do here is to show the products and tell me their stereochemical relationships. So let's see how we do this. Here's our transalkene. I'm just going to kind of flatten it out a little bit like this, because I'm going to add my hydroxyl groups into kind of like a Fisher projection. Now our permanganate could attack from either the top side or the bottom. Flat molecule, permanganate can come in either top or bottom. So let's pretend it comes in on the bottom. That will be our cis 1,2 diol. Now, let's take this and assign stereochemistry to both carbons. I'm going to do that by taking my sawhorse and drawing it like this. Again, the 2 hydroxyl groups are down, so I've shown them both back. Very quickly look at this and tell me if this is R or S. Our priorities: hydroxyl, secondary carbon, methyl, and the hydrogen is front. This is counterclockwise, but the hydrogen is front, therefore that is R configuration. To the bottom. Hydroxyl is number 1, secondary is number 2, methyl is number 3. Again, the hydrogen is coming towards us. This is counterclockwise rotation. So this is also R configuration. Now, when we add to the bottom here, we have R for each carbon. Let's take and let's add our permanganate from the top. Now I'm going to take this, show it in a vertical projection. Now the 2 hydroxyls are pointing up, so I put them here, coming towards us. All right, our top carbon, hydroxyl group, secondary carbon methyl, hydrogen is back. This is counterclockwise, therefore this is S. Our bottom carbon, hydroxyl group is number 1, secondary is number 2, methyl number 3. This is counterclockwise, our hydrogen is back, and this is also S. So, what is the stereochemical relationship between our two products? In this one, both carbons are R. This carbon, or this one, both carbons are S. These are enantiomers. These two are mirror images. Okay, that was a fun exercise here with our transalkene. Let's do it again. Oh, just for the heck of it, I put in the names. This is a butane. It's a 2,3-diol. Both carbons are R. Showing this in parentheses, yes, you can do that. If you don't put in the parentheses, it's not really wrong. A lot of people put in the parenthesis because it just differentiates the stereochemistry from the name itself. So 2R, 3R, butane, 2,3-diol. This will be the same thing, except they're both S. Enantiomers. All right, our cis compound. Just like before, let's take and flatten it out. And let's add our hydroxyl groups from the bottom. We're going to take it. We're going to stand it up. Our hydroxyl groups are both back. Quickly, while I see who just texted me, sorry, assign these two configurations. All right, on our top carbon, hydroxyl is number 1, secondary is number 2, methyl is number 3. Our hydrogen is coming towards us, so we're going to reverse our answer. This is clockwise, making this carbon S. Our bottom carbon, hydroxyl is number 1, secondary carbon is number 2, our methyl group is number 3. Hydrogen is coming towards us. This is counterclockwise, therefore this carbon is R. So, adding to the bottom of our cis alkene, we get S and R. Now I want you to stop and think for a second. What's attached here? Hydrogen, hydroxyl, methyl, right? What's attached here? Hydrogen, hydroxyl, methyl. This one's R, this one's S. What does that make them? That means we have a plane of symmetry. So we have made a meso compound. We don't even have to bother adding it to the top, because if we add it to the top, we would get R on the top, S on the bottom, but it's the same thing. It's a meso. Any questions? All right, let's do a couple more here. Oh, this is 2R3S butane 2,3-diol. Look at these two guys and tell me, are they identical? Are they enantiomers? Or are they diastereomers? Well, right away you know they're not diastereomers because a diastereomer must have more than one chiral center, right? Let's very quickly just assign configurations here. Our highest priority is going to be the nitrile, then the ethyl, then the methyl. Hydrogen is forward. This is going counterclockwise, making this guy R configuration. This guy, cyanide is first, ethyl is second, methyl is third. Hydrogen is forward. This is counterclockwise, making this also R configuration. Therefore, your conclusion is these two are identical. There are two more, same question. Now we have two chiral centers, so they could be diastereomers. Our first one, hydroxyl is number one, the secondary carbon, then the methyl. Hydrogen is forward. This is counterclockwise, so this is R. Our second carbon, hydroxyl is 1, secondary is 2, methyl is 3. This is counterclockwise. Hydrogen is back, therefore this is S. So our first one is RS. Over here, this guy, hydrogen is back, hydroxyl is 1, this is 2, that's 3. We are going in this direction, that is clockwise, so that's R. Our bottom carbon, our hydrogen is forward, hydroxyl is 1, that's 2, that's 3. This is counterclockwise. No, that's clockwise, isn't it? We reverse it, and it's S. These two are also identical. This is the one we did on the previous slide. This is just things rearranged. Very quickly, tell me, are these the same or are they enantiomeric? We already know the first one is R. Nitrile is number 1, ethyl group is number 2, methyl is 3. This is clockwise, hydrogen is forward. This is S. They are enantiomers. This is the one we did on the previous slide. This is another version. Our top carbon, the hydrogen is back. Hydroxyl is number 1, that's number 2, that's number 3. This is counterclockwise. Therefore, this is S configuration. Our bottom carbon, hydrogen is forward, hydroxyl, secondary carbon methyl. That is clockwise, we reverse it, and it's S. So what is the relationship here? These are identical at one carbon and enantiomeric at another. That makes them diastereomers. The operations in stereochemistry are not difficult. They can be tedious sometimes, but they're really not difficult. Very simple review of Grignards. You will see Grignard reactions like these. Again, let's look up top. We're going to take and make our secondary alcohol. The procedure is to split on one side. Look to see what Grignard we need and what carbonyl. The carbonyl is the guy with the OH on it. Benzene ring, one carbon with a carbonyl. That, of course, is benzaldehyde. Our Grignard reagent is just this half, 3-carbon chunk, magnesium bromide attached to the secondary carbon, and it looks like that. Now we could also do this another way, by splitting on the other side. So we're going to split here. Now, our carbonyl was this half. It's attached to an isopropyl group, has a hydrogen on it, so it's an aldehyde. It's going to be this guy. Our Grignard reagent is simply our benzene ring with magnesium bromide attached here. Any questions? One more quick Grignard example here. We are again dealing with a secondary alcohol, so we need an aldehyde. Split this on both sides, pick out your 2 carbonyl compounds. If we split here, we have a benzene ring, 1 carbon, so this again is benzaldehyde. That means our Grignard reagent is this 1, 2, 3, 4 carbon unit with magnesium bromide attached here. And it looks like that. If we split on the other side, we have this unit as our carbonyl. Again, it's an aldehyde, CH2, then a carbon with 2 methyls. I think this will work. Make sure you get the aldehyde, not the ketone. And our Grignard reagent is simply going to be phenyl magnesium bromide. And now you know everything.